Hi guys, in this session I'm going to be covering integration of trig functions, but particularly the two special cases that you're going to deal with. These two special cases are when you're trying to integrate sine squared x and when you're trying to integrate cos squared x dx. So, to get started, we need to have a look at a couple of formulas, which I'll be looking through in the next slide. So, the formula that we're going to be looking at are these ones here, the double angles. And since we're looking at sine squared x dx, what we're going to be looking at here is particularly this one here in the red circle. So we can write up cos 2x equals 1 minus 2 sine squared x. Now what we can do is we can rearrange this. Rearranging this, we are going to get 2 sine squared x equals 1 minus cos 2x, and of course sine squared x would then equal 1 half minus cos 2x divided by 2. Now you might ask this question as to why we can't just integrate sine squared x straight away. Well, if we integrate sine squared x, it doesn't make sense. We need to have it by itself. Anyway, look, let's just do the example and see if it actually makes sense. So what I was trying to tell was, if we try to integrate sine squared x, you would have to do it using a reverse chain rule. But the problem is when you use it using a reverse chain rule, it just won't work out. You'll end up with an answer, but then if you differentiate it, you'll never come back to sine squared x. So anytime we have sine squared x, what we need to remember is what we did in the previous slide, which is on the top right here. Sine squared x equals half minus cos 2x over 2. So what we're going to do is we're going to replace the sine squared x with half minus half cos 2x dx. See, from this point, integrating this is actually very easy, because if I was to integrate half, I'd get half x minus, I'm going to have half there. Now, integral of cos, for those of you that have forgotten, is actually sine. And of course, that will be multiplied by 1 over the differentiation of whatever's inside the bracket here. So since we've got 2x, the differentiation of that is 2. And of course, we have to remember the plus c. Okay, so simplifying this, we're going to get x over 2 minus sine 2x divided by 4 plus c. And that is how you integrate sine squared x. Okay, I'm going to do the integral of cos squared x in the next slide. So once again, to do integral of cos squared x, I'm going to need the double angle formula. And I'm going to look for cos squared a or cos squared x in one of these things. And as you can see, it is right here. So what I can say then is, to find integral of cos squared x dx, I need to use the double angle first. So cos 2x would equal 2 cos squared x minus 1. And of course, as I did with the sine squared one, I've got to rearrange everything here. So rearranging this, I would get 2 cos squared x equals 1 plus cos 2x. And of course, simplifying this, cos squared x equals half plus cos 2x divided by 2. Okay, once I have this, now I need to substitute this into cos squared x and continue integrating as normal, which I'll be doing in the next slide. So here we go. We want to find integral of cos squared x dx. We find out from the previous slide that cos squared x is a half plus cos 2x divided by 2. So now I'm substituting this as the cos squared x, which means I've got integral of half cos 2x divided by 2 dx. Of course, integrating this, again, it becomes easy. So I've got half integrates to x over 2 plus cos integrates to half sine 2x, and that's multiplied by 1 divided by whatever the bracket is, the differentiation of that. So in this case, differentiation of 2x would be 2. And of course, we have to remember our constant. Okay, Simplifying this, we're going to get x over 2 plus sine 2x divided by 4 plus c. Alright guys, that's pretty much the two special cases covered here. So anytime you see integral of sine squared x or cos squared x, remember that you need to rearrange them as a double angle, and then you can actually integrate them. Alright, that's all from this session. Thanks for watching.